Yeah, 10, we did 10 in class earlier. It was number 52. Number 11, we have tangent minus 1, tangent plus 1. We have to make it look like 1 minus cotangent, 1 plus cotangent. Now, many of you guys, just like myself and like Shimke did, a lot of us saw tangent and said, ooh, sine over cosine. And if you did that, it got you into sine over cosine minus 1 over sine over cosine plus 1. You got common denominators, and all of a sudden, if you simplify it out, you wind up with sine minus cosine over sine plus cosine. And then you're like, it don't look right. And there's really not much you can do from there. You can try and work through some reciprocal properties and multiply out again with common denominators. It just gets to be an awful, awful, awful thing. But if you look at how you're starting with tangent and you're ending with cotangent, aren't they reciprocal properties of one another? So instead of writing tangent in terms of sine and cosine, write tangent in terms of cotangent. And then get your common denominator. Because when you get your common denominator now, what's it going to be between cotangent and 1? Cotangent. Fraction on the left has a cotangent. Fraction on the right needs a cotangent. See where I'm going with that? And it drops right away. Same deal with the denominator here. You have cotangent for your denominator. Fraction on the left has it. Fraction on the right doesn't. And then we have a your lotion smells good. Sorry, random, but it does smell good. Devin, you can't tell, but it smells nice. Just gotta keep him involved. Make sure he's not sleeping. You're not sleeping, are you? Okay. So now you have fraction over fraction means you're going to multiply by its reciprocal. You guys will be sad next year when you're not teleconferencing with somebody, because then you would randomly yell at somebody. Oh yeah.
We can still yell at it. That's me in person.
That's right. And then you're done. Yes, sir. What do you mean? Like multiply it by 1? On top and bottom? So basically, so you're multiplying by tangent over tangent. I see where you go with that. Yes, that does work. That's another way of doing it. Yeah, it does the same thing. Mm-hmm. Because if you divide by tangent, you're multiplying. What you're doing is this. You're taking. You did this to both top and bottom, kind of. It works because you're distributing that through. That works. It's another way of doing it. I didn't. Somebody else brought that up. I think this morning. I never thought of doing it that way, but it works. Yep, works. Because if I distributed that through, that works fine. Yep. Yeah, like I said, there's many, many, many ways of doing these things. Steal yours for a second. I saw you did like a. Oh, that was the way you did class. I didn't know which number that was. Yeah. I want to see how you did one because I saw all that work. Oh, what did she do? Yes, ma'am. You have $1? We did it yesterday in class.
I didn't think we did that one.
Yes, it was number 52. It's in the same. It's the same problem as number 52, just in a different order. Yes, sir. I do not have a pen or a pencil. I have a Sharpie. Can we have a pen or a pencil? Yes, ma'am. 16 sucks. All right, hold on a second. Nina, we did 52 yesterday. It's the same thing. The only difference is tangent, cotangent came first. It's the same problem. 12 you were saying? We'll do 12 first, then we'll go to 8, and then 16, and then whatever's left over. Now, this one is actually relatively quick. Okay. Now, when you have one like this, in the back of your mind, you sit there and start thinking, okay, if I start splitting things into sines and cosines, you get common denominators and go through all that. It'll get you there, but it's a bit of a mess. In this case, what is 1 plus tangent squared? Secant squared. So right away, I would rewrite this as over secant squared, because what can I do now that I have a singular term in the denominator and 2 on the top? Split. I can split them up. Now, I'm going to rewrite everything in terms of sines and cosines. What is 1 over secant squared? Cosine squared. All right, it's cosine squared. And then I have sine squared over cosine squared divided by 1 over cosine squared. And when you're dividing by fractions, you're going to multiply by their reciprocal. So what happens with the cosines on the right-hand fraction? They all die, sure. So you wind up with cosine squared minus sine squared. And the next trick is something that you're going to use a lot over the course of the next few days. At this point here, you need to get sine squareds. How do you rewrite cosine squared in terms of sine squared? Bing, 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 bing. And how many sine squareds do you have? This is a very common, this part here is very common. This is the type of problem that we're going to start looking at today more when we talk about equations. Yes, sir? We're not going to the right side. You have to go left to right to show. You can't just add stuff over and show that it equals 1. You know, or you add, what did you add 1 sine squared over and show that cosine squared equals 1 minus sine squared? I see what you're saying, but you want to. Your rule is to verify everything on the left turns into the right. Don't touch the right at all. Right? I want you to go left, right. Everything I give you is going to go left, right. Okay. Yes, ma'am. No. Many, many, many ways. Many ways. It's fine. Did you break it down right away in sines and cosines at the beginning? Yeah, it's fine. If you want me to look at it later, we'll have a little bit of time. I'll be more than happy to look at it for you. But there are so many ways to do some of these things. Don't think that the way that I'm doing them is the only way. When I do these problems, I try to think of it in the most generic way. Bless you. And that's fine. That is absolutely fine. There is nothing wrong with that. Okay. We just did. What was next? 8. This is one that Shimke was working with here. This is another little short, a little weird one. So this is another one of those little weird ones. Notice how it's going from, a lot of times when we had problems when it went from addition or subtraction to multiplication, you had to get common denominators. But what happens when you go multiplication to subtraction, you don't need common denominators. What you need to do is figure out how do you break one of these parts into 2 pieces so that way you can distribute. So when I'm looking at this one, I have to think about a way that I can rewrite either tangent squared or sine squared into 2 pieces. Well, if you go into it, the easiest one to write would be sine squared is 1 minus cosine squared. If I do that, I get tangent squared times 1 minus sine squared. I'm sorry, cosine squared, excuse me. And now I just have to distribute. If I distribute this, I get tangent squared minus tangent squared cosine squared. But what is tangent squared? Sine squared over cosine squared. And was I correct in assuming that most of these weren't as awful as they were the day before? 16 sucked. Wait a second, 16 was awful. Out of all of them, I think 16 was the trickiest. Okay? Yes, sir. With one? Oh, yeah, I'm sorry. Real quick, let me go through 3 real quick for them. Then I'll go to the other one. Ladies and gentlemen. Now, in this one here, you've got a potpourri of trig functions, which means the easiest thing to do is just to rewrite everything in terms of sines and cosines. If I do that, I get sine, well, I get 1 over cosine times sine over 1 over sine over cosine, oops, plus cosine over sine. All right, just splitting everything apart. Did you put a time sign? There you go. Now everything drops because then you get common denominator. Here you go. From here, this is just sine over cosine. Here, you have to get the common denominator. Put the common denominator together, you get sine times cosine, or excuse me, cosine sine, if I write it left to right. Then I get sine squared plus cosine squared. Moving all that up, that sine squared plus cosine squared becomes 1. And then I just wind up with times cosine sine, and I get sine squared. Yes, ma'am. For which one? Oh, when I get the common denominator, it's got to be cosine times sine. So this one needs a sine, this one needs a cosine, cosine squared, cosine squared. Yeah, I just wrote this. This becomes 1. I already did 10. We did 10 yesterday. Ten is the same problem as 52, just the order is switched. It's the exact same problem. Last one, 16. And I wouldn't say this is the worst one. This one takes a little bit longer than the other ones because you've got a whole bunch of sets of common denominators to get. So, in order to do this problem, you have to get common denominators twice. You got to do it for the numerator and then for the denominator. So, split that out, you get sine over 1 plus sine over cosine all over 1 over 1 plus 1 over cosine. You okay with that? Now, the common denominator up here is going to be cosine. Fraction on the left needs 1. Fraction on the right doesn't. So we get, bless you, we get cosine sine plus sine. Same deal on the bottom. Common denominator is just going to be cosine. Fraction on the left needs 1. Fraction on the right doesn't. I'm going to have to multiply by a reciprocal here at the end. But if I look at my first numerator, yeah! What do these guys have in common? And now when I bring up the bottom, I multiply by the reciprocal, and what are you left with? Right. Welcome to April. Oh, now, here's where things get interesting. What happens now is that, and I know I've said this before. I think you're like, well, I know I've said a little bit this before. A lot of this stuff really is, how do you fight your way out of a problem? How do you think your way through something? How do you solve something? How do you simplify a set of values in front of you? How do you algebra? What we're going to use a lot now is going into this. We'll do this. And today when we talk about solving on the interval between where x is between 0 and 2 pi. And we're going to utilize these trig identities and some of the trig properties or Pythagorean identities in order to solve equations. And what's that? Yeah, because today we're talking, remember how we used theta, we used x, we're going to solve for the value of x. So today I'm going to not try to be lazy and not use, and I'm actually going to write it in. So when I do this, we need to start thinking about how we've solved equations with trig stuff before. In order to do that, we had to get one side equal to 0. That doesn't change. So if I move to set a side equal to 0, I'm going to go and say that we have 2 cosine squared x minus 3 sine x equals to 0. But the problem is we can't solve for both sine and cosine at the same time. So we have to think of a way to rewrite one of the trig equations in terms of the other. Yes, sir. Perfect. And that's where we're going to see a lot of it. We're going to see these trig identities come back and forth, where we're going to use sine squared plus cosine squared is 1, 1 plus tangent squared is secant squared, 1 plus cotangent squared is cosecant squared. We're going to use some manipulation of those three trig Pythagorean identities to solve the problem. So just like you said, I can rewrite cosine squared in terms of sine squared by saying that, well, cosine squared is 1 minus sine squared. Now what do? You don't cry. After, all right, how about this? After you, that's what you say. After you stole your line, after you're done crying, the next step would be to, exactly. It's real in here. Now, when I go to factor stuff, do you want your first term to be negative or positive? Positive. So would it be okay if I multiplied everything here by -1 and just rewrote it in descending order? I hope so too, because that's what I'm going to do. So I get 2 sine squared x plus 3 sine x minus 2 is 0. And now you're back to a problem we've done a couple of weeks ago. And if I'm not too mistaken, you guys did these just fine. You did. Because now remember, at this point here, you can do, guys, I've got like 4 examples we've got to get through here, okay? One of the things that you guys have done before, if you want to use that trick of that U substitution to keep it clean, go for it. If you don't, who cares? Because it's the same process. This from here on out is just algebra. What times what is -4 that you add together to get 3? 4 and -1, okay. So we have 2 sine squared x minus 1 sine x plus 4 sine x minus 2 is 0. A lot of these problems are going to turn into some quick factor via grouping. But you all know how to do. The only thing that's different is that there's more letters involved. It's the same thing. Okay? GCF them. Well, let me rephrase that. Get the greatest common factor of them. Yeah, thank you. That should be a math team t-shirt. Just GCF them. Come on! At least you would have laughed at that. Devin, you thought that was funny, right? Shut up, Devin. Are those two things in parentheses the same thing? Yes. Oops, sorry. Sorry. And now it's to the point of what angle has a sine of 1/2? What angle has a sine of 1/2? What angle has a sine of -2? Sine is 1 over what? Okay, so that means my opposite is 1, my hypotenuse is 2, which places me at what angle? 30. 30 degrees is what in terms of radians? Pi over 6, good. So I'm at pi over 6, and where else is sine positive? Second, so what's the angle in the second quadrant? Those are your answers. And then I go to the other part. What angle has a sine of -2? Right, can't do it. There is no such angle. Yes, ma'am. Notice it becomes the same exact problem that you've done in the past. The only thing that's going to change here, guys, is that it's going to add maybe a step at the beginning. Okay. All right, let's try this one. Huh? Same deal. Same deal. Yes, sir.
Would we also have to solve for cosine here?
No, because what we did is we rewrote it in terms of sine. And by using the identity, you're eliminating having to worry about the cosine. Would be a bad idea. So in this case, guys, I still have 4 to go. You're taking way too long. Yes, I know it's April, it's sewing. Who cares? If we don't get through all these things, the other examples are in first hours, just so you know. In this case here, when you have tangent squared and secant, it's forcing you to use which of the 3 trig Pythagorean identities? The one with the tangents and the secants, right? It's kind of nice how it's convenient. Also, when you have a squared term and a non-squared term, it kind of tells you to rewrite the squared term in terms of the non-squared term. So, tangent squared can be rewritten in terms of secant by, there it is. You get 2 secant squared minus 1, and guess what happens? Everything from here is the same. It's that first step that you have to adjust for when you're dealing with the trig stuff. If they're different trig functions, you have to just rewrite in terms of 1. And more often than not, if it's a squared and not, rewrite in terms of the not. So you get 2 secant squared x minus 3c. I'm putting these in order real quick. It's the same stuff. And then for lack of time here, I'm assuming you guys can do what times what is negative 4. I can do it. What times what is negative 4 to add together to get negative 3? Negative 4. You'll also find out that a lot of these are going to be the exact same factor style parts because there's only so many angles that make this stuff work cleanly. Okay? Because if you get into all these other weird stuff, you'd have to have a calculator, and what don't we have? So why force it, right? Let me show you set up on a weird one. When I finish? Well, this one's in terms of secant. Okay, I should probably do this one because it's an oddball with the secant here. Well, we'll do this one here. So you get 1 times what was negative 4, you add together to get negative 3, negative 4, and positive 1. So I'll go 2 secant squared x minus 4 secant x plus 1 secant x minus 2 is 0. Just split it apart like we've done before. And now I want to get GCFs. When I do GCFs, I'm going to have a 2 secant and a 1. And I get those 2 parts. And thanks for reminding them, it's a secant problem. We haven't done a secant one yet, so it'll be good. Those 2 parts are the same that are in parentheses. That's always a good sign. That means you're doing it correctly. So you write that part down. Does that equal 0? At this point, you're still going to get the secant of x equaling something on both sides. So I have to add 2. I have to subtract 1 and divide by 2. And I don't want to go any further until I get rid of my inverse trig identity. What I mean by that is, I don't want to try to figure out what angle has a secant of 2. I'd rather figure out what angle has a cosine of 1/2. Because if I inverse secant, I get cosine. If I inverse 2, I get 1/2. It's an easier way to do it. Your minds are made, the way that we've always worked with our unit circle stuff, we were always working in terms of cosine, sines, and tangents. So when you get to this part here, reciprocal both sides to work with cosine, sines, and tangents. That's how your brain will think. It'll be easier to go that way. Do you have to? No. Is it easier? If I flip these reciprocals, I get cosine x is 1/2, and the other one was it's hiding. It would be cosine of x is -2. Can I do that? Cosine of x is -2? Nope. I know right away that's not going to work. But I do know that I can say what angle has a cosine value of 1/2. That means my adjacent is 1, my hypotenuse is 2, which makes me a 60, which is pi over 3. And where else is cosine positive? The 4th quadrant, so you're at, I heard you say it was 5 pi over 3. It's not that it's not that any of the stuff that we have done has changed. What's changing here, guys, is that very first step of of just rewriting things as one part. Sorry that you have to sit next to me. And you. All right, let me show you a weird one.
Not your friend. Only friends or sisters.
In this one here, you got a lot going on. You have a cosine tangent minus 2 cosine squared. Oh, put it away. You have cosine times tangent minus 2 cosine squared. What's cosine times tangent?
Yeah.
Cosine tangent, very good. Isn't this the same as saying cosine times sine over cosine? Every once in a while, they'll put something in there that you have to do a simplification prior to using a trig identity. And that's usually what's going to happen when you see a whole bunch of stuff, like 3 different trig functions as opposed to just 2. Right? Not difficult, just simplifying cosine and tangent, that's pretty easy. If we stood there long enough, we would have figured it out. But, whatever, stood, whatever, sat. Now, what do I rewrite? Sine or cosine squared? Cosine squared. I know, but you meant in terms of sine is what you were saying. Okay. I was with you. So cosine squared is the same as what in terms of sine? 1 minus sine squared. What are you going to screw up at this next step? Distributing the negative. This is the problem right here that I guarantee you will screw up, is you'll forget to distribute the negative. It happens over and over and over again. We'll get sine of x minus 2 plus 2 sine squared, and I would bring the 1 over. All right with that? Please be careful when you have it distributing the negative. I know that it's not a difficult thing, but I know that's where you guys will mess up. I think we've said that every time that we've seen it.
Somebody still does it.
So that somebody,
Stop doing it.
I don't know who that somebody was. Somebody recently did it. Next time we won't blame you. We should, well, yeah, we'll blame Shimki. Descending order. And what times what is negative 2? You add together, you get positive. Oh, I was a negative. Grouping wise, setting this up, I know you guys can do that. I'm not worried about that. I just wanted to show you one other style that does show up today. And it's actually another thing that you've done before. Right? For example, is it okay if I stop? I know a lot of you guys are focused. Screw you, Murphy. I'm going to finish the problem because I'm going to do. Because that's what you guys do. Some people do. I'm going to ask you this. What do you do here? Wait. Multiply everything by x, right? If you multiply by x, what happens? You get rid of the denominator. So you get 2x squared plus 1 minus 3x is 0. Okay? What would you do here then? Exactly. That's exactly right. In this case here, a lot of times when they have, notice neither of these are squared. When you have reciprocal functions that are not squared, it's forcing you to multiply by the main term, or one of them. Because if I rewrite this problem in terms of sine, which is our standard trig function, I'd get 2 sine x plus 1 over sine x is 3. Well, to get rid of that denominator, I would multiply everything by sine of x. It's the same problem that you've done before. It just has more letters. So you get 2 sine squared plus 1 minus 3 sine x is 0. And guess what happens? It's the same thing. Oh. The only thing we're changing here, guys, is the first step. Quite honestly, that's all that's different. Everything else has been the same, which you guys did this stuff fine. And all we're looking at today is going to be stuff on what we call the general solution, not general, excuse me, on the interval. Okay. Let me give you the problem. I just wanted to make sure I got to show you that trick here. I'm a great singer. I apologize for my interval notation. I accidentally said less than or equal to 2 pi when it's just supposed to be less than 2 pi. She is. Now, on this one here, you've got 2 columns. Which of the 2 columns do you think I'm going to ask you to do today? The one on the left. Reason being, what did we just do a whole bunch of in class? On the interval problems. So we'll do that, and tomorrow we'll revisit some interval stuff, put everything together. Just a little FYI, I'm starting to see a lot more light at the, at the light at the end of the tunnel as the end of the school year. I'm starting to think that this might be the one time I might put the quiz on a Monday. I haven't had one the entire year with you guys, and I might, instead of being on Wednesday after the SAT, because it's still on after another day off, I might move it to Monday, and tomorrow will wind up being a whole bunch of just revisiting everything and going and going and going and going into that. It's not my favorite thing to do, but due to the lack of time that we're running across now, yeah. As in like 4 days. So, okay. What's that?
Yeah.
Not move. I'm starting to think that it's kind of one of those things that I have to do that just because of time. Because honestly, you don't want me to break this out and start graphing and spend 2 weeks graphing and then have you remember how to do all the simplifying and verifying and solving equations along with graphing at the same time. It's a natural, it winds up being a natural break. It just sucks that the SAT is that Tuesday. And then because nobody will be here on Tuesday, and then it would be an extra day off. And so we take 2 days off, review, a day off, and a quiz, and then all of a sudden we've only got 2. We get further behind with junk. I'm gonna look at what I have as far as I wrote out a bunch of questions in terms of what I'm looking at for the quiz, and I've done them already. I'm gonna kind of see if I need to cut and go through there. I'm looking at maybe like 6 questions. All right, nothing too nutty. Yeah, I'll give you the whole time. Yes, ma'am.